We want to find the limit if it exists. We have the limit of x comma y approaches 2 comma 1 of the quantity x minus 2y divided by the quantity x minus 2y squared. So the first thing we should recognize here is that we cannot find this limit performing direct substitution, because at the point 2 comma 1 we would have 0 divided by 0, which is indeterminate, which means to find this limit or see if it exists, we'll have to determine the limit along several paths that approach the point 2 comma 1. So notice on the right here I've graphed the point 2 comma 1 on the xy coordinate plane, and I've also graphed several paths that we could use that approach this point. To start with, let's use the two most obvious paths, which would be y equals 1 and x equals 2. Now if we find these two limits along these paths and they're not equal, we can conclude that the limit does not exist. If they are equal, that does not tell us the limit does exist. That means we'd have to consider additional paths before we conclude the limit exists and what that limit would be. However, it is often helpful to graph the function and analyze the surface when determining limits of functions of two variables. And I've provided the graph of our surface here below. Notice how the graph of the surface looks strange along this path here, which if we take a look at our function and recognize that we'd have discontinuity when we have division by 0, so we set the denominator equal to 0, so we set x minus 2y squared equal to 0, and solve for x by adding 2y squared to both sides, we'd have x equals 2y squared. So graphically what we're seeing here are these are the points where we have division by 0, and therefore the surface has discontinuity. So this is something that can be helpful if we notice this. But again, what we're going to do now is consider the limit along the path y equals 1 and x equals 2. So for the path of y equals 1, we'll substitute 1 for y, so we'd have the limit of x comma 1 approaches 2 comma 1 of, again, if y equals 1, our numerator would be x minus 2 times 1, or just x minus 2. Our denominator would be x minus 2 times 1 squared, which is also just x minus 2. Notice here we can simplify this rational expression. X minus 2 divided by x minus 2 equals 1, so this simplifies to the limit of x comma 1 approaches 2 comma 1 of just 1, which of course just equals 1. So we've shown along the path y equals 1, the limit would be positive 1. This does not mean this limit equals 1 or that it even exists. We must consider additional paths. Now let's consider the path along this vertical line, x equals 2. So for the path x equals 2, we'll now substitute 2 for x. So we'd have the limit of 2 comma y approaches 2 comma 1 of, so if we substitute 2 for x, notice how we'd have 2 minus 2y divided by 2 minus 2y squared. This is going to simplify. Let's do some algebra down here. If we factor out 2 from the numerator, we'd have 2 times the quantity 1 minus y. In our denominator, we'll factor out 2 as well, so we have 2 times the quantity 1 minus y squared. Notice how our denominator is a difference of squares, so we have 2 times the quantity 1 minus y divided by 2, and then we have a difference of squares, so we'd have the quantity 1 minus y times the quantity 1 plus y. And now when we simplify, notice how we have a common factor of 2 as well as a common factor of y minus 1, so this simplifies to 1 divided by the quantity 1 plus y, which means now we have the limit of 2 comma y approaches 2 comma 1 of just 1 divided by the quantity 1 plus y. So notice as y approaches positive 1, our limit would be 1 divided by 2, or 1/2. And we can actually stop here because notice how we did not get the same limit. The limit along the path x equals 2 is 1/2. The limit along y equals 1 is 1. And for this limit to exist, the limit along all paths approaching 2, 1 must be the same, and since they're not, we know this limit does not exist. Okay, I hope you found this helpful.